welcome to the NPTEL online course on Smart Grid today, and we will be talking about
operation and control of AC/DC hybrid microgrid.
As we all know, during last few lectures, we covered important concepts related to AC smart grid operation and control, and further we moved to DC smart grid operation and control, and today we wish to discuss very much in detail the challenges associated with operation and control of AC/DC smart grid. Now, my dear friends, the very important issue here, when we talked about AC smart grid, we understood what are the control mechanism, operational mechanism when it is connected to grid and also in autonomous or islanded grid of operation, and similar kind of analysis we have understood and discussed in detail related to DC microgrid or DC smart grid too. But today we talk about a grid which has both AC smart grid as well as DC microgrid, DC smart grid in place. So, imagine a grid which can act as a both AC and DC smart grid, or they are together, and both AC DC smart grid now can act in line with the utility or the grid connected mode, or it can also operate in an islanded mode. Now, why we are looking for AC DC smart grid? Most of the generations in specific to PV and fuel cells, they do generate power in DC mode, and then we need to convert to AC if you connect to a AC smart grid. Similarly, if it is a wind generation, that power being generated at AC, and then we need to convert that to into DC if it is a DC smart grid. Further, the loads today are of both DC and AC type, though most of them are of DC type, but still we cannot ignore the AC type of loads which are very much important and industrial specific loads, and those loads need to be catered by both AC smart grid as well as in DC smart grid under any given platform or conditions. So, if it is a DC microgrid or DC smart grid, that DC loads can directly be connected, whereas AC load needs conversion. In case of AC smart grid, AC load can be connected and DC load need to be converted. So, we could see there is a bigger challenge of DC to AC and AC to DC conversion in case of AC grid, and AC to DC and DC to AC conversion in case of DC grid. And those conversions are more and more significant in case of a independent AC or DC smart grid platform. So, to gain a couple of benefits and to avoid multiple conversions, researchers thought of going for a hybrid grid or a combination of AC DC smart grid, and that is what the today's topic is all about. But we cannot ignore the challenges. Now, there are very important challenges. AC smart grid do operate with different control schemes, different operational schemes. DC grid operate in a different control schemes and operational schemes. When they go together, what would be the common control scheme that need to be adopted, both in case of islanded as well as grid connected mode. So, we will slowly proceed to our understanding in detail what are the challenges and how that can be addressed. Certainly, AC/DC smart grid is a real merit over individual AC/DC smart grid, but the control challenges become severe, and we will look forward to address those issues during next 30 minutes from now. The background of AC microgrid is mainly proposed to facilitate the interconnection of renewable to conventional power system to reduce generation from fossil fuels and this requires the conversion of many DC sources such as PV and fuel cell to be converted to AC, and hence we need DC AC conversions. The main bus in case of a AC microgrid is AC. The AC microgrid is connected to the utility grid for excess deficit of power sharing and for increasing the reliability of the load. Means the AC smart grid has to be connected with the grid, so that as and when the load increases, we can take power from the grid, and when it is decreases, we can share power to the grid, and that increases the reliability and the robustness of your AC smart grid or AC microgrid. In case of main grid failure, all the connected DGs and loads need to communicate in the AC platform, because it is purely AC grid for you. Modern electronic loads work on a DC platform, and in this type of microgrid, DC, AC and further DC conversion stages are more common, because you generate power with DC, connect to your AC grid, try to cater your loads in DC. So, DC to AC, AC to DC. So, that those type of conversions are very common in case of AC microgrid. Now, similar, let us see what is DC microgrid in specific. The recent surge in the concept of DC microgrid facilitate direct conversion of renewables like PV, fuel cell, also DC loads. Means just imagine you have a system where you have huge amount of PV connected, as well as you have the loads which are purely lightning, and a DC microgrid is wonderful, because you can take all the energy in the form of DC and then cater all your loads in the form of DC, though the voltage uplifting or downgrading has to be done, but certainly it is a purely DC platform. The main bus, which is DC, the DC microgrid is connected to your main grid to exchange power, so that the reliability of the system can improve with variation of the loads. In case of main grid failure, we can operate in a islanded mode, and all the connected DGs and loads need to communicate and exchange power in the DC platform. However, the DC microgrid alone does not allow direct interconnection of renewable like wind. For example, if you have a DC grid in place and you have wind generators, and those cannot be directly connected to your DC grid. So, perhaps you require AC to DC conversion, and being said that we can have loads, industrial loads, induction machines, those are again AC in nature. So, again you need DC to AC conversion. So, in case of a DC smart grid or microgrid, you need to have AC to DC and DC to AC conversion, which is very common. Now, if you move to a AC DC microgrid, which is the combination of both AC as well as DC microgrid, then the main buses are common buses are of both AC as well as DC. So, you will have a AC bus in place, you will have a DC bus in place. Okay. The hybrid microgrid is connected to the utility grid for excess or deficit energy sharing or power sharing, and for increasing the reliability of the load. So, even this AC DC microgrid, hybrid grid has to be connected to my grid, so that the power exchange can occur as and when the load is keep on varying. In case of the main grid failure, my AC DC hybrid microgrid can act independently in an islanded mode of operation, and all the DG distributed generators need to communicate to each other in both AC as well as in DC platform. It is a combination of AC and DC microgrid, and very popularly named as hybrid microgrid. Both AC and DC microgrids contain distributed generators, loads, and maybe storage elements or storage systems. So, you may have a AC microgrid or AC smart grid, which may have its own distributed generators, loads, as well as storage systems. Similarly, the DC microgrid may have all three components like distributed generators, storage elements or systems, along with loads which are either AC or DC type. both the microgrids are connected together through a single AC-DC inverter, which helps to transfer excess or deficit power from one microgrid to the other. Now, please try to understand. Let us say my AC microgrid may have excess power that need to be transferred to my DC, and vice versa. I may have a DC microgrid which may have excess power that can go back to my AC grid. The main control objective of AC-DC hybrid microgrid is to achieve power balance within the individual microgrid most of the time, because we have to balance your AC-DC microgrid even you are along with the grid, but you have to balance your energy very frequently. Now, there are different type of architectures available in literature, but I felt very comfortable in picking up two very common architecture, perhaps that address all type of different architectures. So, one of the very common architecture is AC-DC coupled hybrid microgrid. We call it structure 1, and then we will see one more structure which is structure 2 in the later stage. Now, I need your attention here. Let us say this is the DC grid or a DC bus, and this is my AC bus. Okay, means this zone belongs to my DC microgrid, this section, and this zone towards the right belongs to my AC microgrid. And then we have an important utility grid. Now, both AC-DC hybrid microgrid can connect along with the utility, and during emergency this can also get disconnected, and this can operate in your isolated or islanded or autonomous mode. Now, in case of a DC bus, we have all different type of sources, that is DC distributed generations, AC distributed generation, and SC, that is storage elements. And because it is DC in nature, the DC distributed generators can directly be connected to DC bus through DC-DC conversion. AC distributed generation can be connected to my DC bus through AC-DC conversion, and whereas the storage element can be connected to my DC bus through bidirectional converter, because it may have to discharge its energy to the grid when required, as well as it has to charge as and when required. So, that is what it means bidirectional conversion presence. Now, in case of the AC grid, similarly we do have the grid is AC and we have AC distributed generations. So, that can be connected to my AC bus. Similarly, the DC distributed system can be distributed generation can be connected to my AC bus, and the storage element also can be connected to my AC bus. Now, let us concentrate on the load side. Now, the loads can be either of DC and AC type. So, both DC loads as well as AC loads can be connected to my DC bus. So, the DC loads can be catered directly, whereas the AC load need to be catered after DC-AC conversion. Now, looking into the AC bus, the loads could be AC and DC load, and this AC load can directly be converted here, and similarly we can have a conversion that is AC to DC, and then we can cater to the DC load. So, this option is also possible. And being said that, end of that, both DC and AC bus will be connected through a interlinking converter, that is ILC. So, where the energy or power exchange is possible from DC to AC type as well as AC to DC side. So, this conversion is possible through ILCs. Now, in this structure 1, what are the key features? Both DC and AC buses have distributed generations as well as storage elements, and these buses are linked by interlinking converters, that is ILCs. The AC-DC coupled hybrid microgrid has distributed generations and storage on both AC side as well as in the DC side. There is a need of robust coordination between the DC and AC subsystem for the voltage and power control. In general, the structure is considered if major power sources include both DC and AC powers. However, DC AC DC as well as AC DC AC conversions are inevitable, means you cannot avoid in this type of structure, as both DC and AC sources and loads are connected to both the buses. Because in the DC side you have DC AC loads as well as DC AC generations or sources along with the storage. In case of AC grid, you have AC DC distributed generators, AC DC loads as well as your storage elements. So, I mean the conversion from DC AC DC as well as AC DC AC is certainly cannot be avoided. But we can also imagine some structures of or the architecture of AC DC microgrids or smart grids, where we may connect all the DC sources to a DC bus and all the AC sources to a AC bus, and very carefully we can distribute the loads, DC load to the DC side and AC load to the AC side. That is one of the wonderful structure one can ever imagine. If you could manage to connect all the DC sources to a DC grid, all the DC loads to a DC grid and AC source to a AC grid and AC load to a AC grid. So, that means both the grids are taking care of their own common bus characteristics for both generations load and the bus, if it is purely AC or purely DC, and further they can be connected to ILCs where the exchange of power is possible as and when required. That is certainly an efficient way of imagining the smart grid structure. And this is another structure, we call it is structure 2, where you all can see this is my DC microgrid, the left half, and the right half is my AC microgrid, and we can clearly observe that the PV, battery, ultra capacitor and DC loads, all DC characteristic based generations and loads are connected to my DC bus. Now, similarly, if you look at the right side, the AC microgrid, all the AC loads, diesel generators, utility grid, wind system, which are purely AC operational, connected to my AC bus, and perhaps they have been interlinked through DC AC conversions. And this is one of the very efficient structure where we have DC one side and AC one side. Previously, we have seen one more structure where AC bus can accommodate all types of generators as well as loads, and DC bus also can accommodate all the type of generations and load. Both the structures are very important. Now, in case of structure 2, there are few merits that let us discuss. Mainly AC sources and loads are connected to AC network, whereas DC sources and loads are tied up with the DC network. This structure has the key benefit that the process of multiple DC AC DC and AC DC AC conversion will certainly be reduced significantly because of an individual AC and DC grid. This structure improves overall efficiency and reduces the system cost with reduced number of power converters by connecting sources and loads to the AC and DC buses with minimized power conversion requirements. Now, slowly let us move into the control strategies and power management schemes. Now, for the operation of hybrid AC-DC microgrid, control strategies and power management schemes are the most important aspects. The power management strategies determine output active and reactive power of the generators connected to my AC-DC grid from the diesel generator and storage elements, and control the voltage and frequency at the same time. Now, you see, when we get into the DC side, a DC microgrid control operation, where we realize that the frequency element is missing, so the droop characteristic need to be redesigned. In case of AC, all options are possible to me, but in case of hybrid, now I have to see what would be my common control characteristic that can take care of both the grids simultaneously. Now, what are the challenges that we do see when we integrate both AC and DC smart grids together? We realize the benefit, now the challenges. Due to the absence of global variable, because we do not have a common variable to take care of both DC and AC, which can be used for power sharing, voltage and voltage regulations or frequency regulations. In autonomous mode of operation, when it is islanded, power sharing between AC and DC microgrids cannot be achieved by conventional PF or QV droop control characteristics. Power management system, that is PMS, should share the power demand between the existing AC and DC sources by a specified droop method. As nonlinear loads are also part of this microgrid, harmonic power sharing should also be taken into account between the grids. A trade-off between reactive power sharing and voltage regulation become important. The specified droop control should be independent of line impedances between the inverter and common AC-DC bus. For proper load sharing among the AC-DC sources, a robust energy management system can be employed to maintain optimality and reliability of the microgrid. Now, let us see what are the operating modes of the grid. There are two modes, as we all know, one is grid connected, the other one is isolated. Now, in a grid connected mode, the power management strategies can be classified into two ways. One is dispatched power mode and the other one is undispatched output power mode. Now, let us focus. Now, imagine we have both AC and DC smart grid or microgrid in place together, and both AC DC microgrid is now being connected to my utility or the main grid. Now, the power management strategies, because as and when the grid needs power or we have excess power in your AC DC smart grid, that need to be given to my grid, and when it is shortage or deficit, then we need to take it from the main grid. Now, during that grid operation, there are two challenges with me here. Now, the main grid can use that AC-DC microgrid as a component to get major benefits of its own voltage control and frequency control mechanism. Let us say my system is suffering with loads, an excess load, so I am shortage of power, so I can take energy from the AC-DC microgrid, and similarly I am excess frequency and I can give back to my microgrid for storage and charging them. So, that is one way of, so where actually the generations of the AC-DC smart grid can be controlled, whereas in case of undispatched output power mode, we perhaps feel that we give all our energy, operate all my generators in MPPT mode, and whenever you have excess power, you try to feed the grid, So, the most important is dispatch power mode, where your generators of the AC-DC as well as the storage, they keep on varying to meet the grid requirement. And in case of undispatched output power mode, where you do not do much, you fix your generation at their MPPT mode and keep on generating, and if your loads are less, then you give to the grid. So, that is what both the methods are very commonly used. Now, in dispatched power mode, the power exchange between the microgrid and the main grid is dispatched from a higher level control or optimization scheme, whereas in case of undispatched output power mode, the microgrid output power is not dispatched. In case of dispatched power mode, the microgrid behaves like a controllable source or load to the main grid. As I mentioned earlier, all the loads or generators connected to my AC-DC hybrid microgrid act like a controllable source or a load, so that the main grid can provide, it can provide the valuable support to the main grid. And to realize this, storage elements are inevitable. Means if you like to vary your generations as well as load of your AC/DC microgrid to meet certain requirements of your main grid, then the storage has to be there, because all the variations, because the discharging and charging of storage can perhaps meet out a better requirement of your main grid. Now, in case of a dispatched power mode, distributed generators and storage elements operate on power control mode. The power control can be realized by either current control or voltage control. Now, in case of current control mode, which is popularly used in grid connected operations, distributed generators output current is controlled in order to track the reference power, and the output voltage and frequency are determined by the main grid. Now, let us move to the voltage control mode. In a voltage control mode, which can be used in both grid connected as well as in islanded operation, distributed generators output voltage is controlled to regulate its output power, and distributed generators behave like a synchronous generator to me. Now, to produce the dispatched microgrid output power, power balancing schemes within the microgrid are used to share dispatched power among input power sources. For example, renewable energy based distributed generators can work on their maximum power point MPP, and other power sources can provide power deficiency between generations and demand, considering input power sources operating range, response, etc. Means to highlight, in case of AC/DC microgrid, you can control your generations to meet your main grid requirements, or you can operate them in constant or MPPT mode to simply cater to the grid or exchange your energy if it is excess. Now, in case of undispatched power mode, the generations are not dispatchable or frequently varying. In grid connected undispatched output power operation mode, all generated powers are fed to the grid. Whatever the power you generate, that all will be fed to the grid. Distributed generation work on MPPT, and storage elements are typically charged. Storage elements are typically charged. So, you generate, charge your storage and exchange to your grid. That is what you do. But in case of a dispatched power mode, where actually you keep on controlling your generators even within the AC/DC microgrid, so that the standards of the voltage regulation of the main grid can be obtained, and sometime if you like to vary your loads within the AC/DC microgrid is also possible. Moreover, the storage elements can be controlled to smooth distributed generators output power oscillation, especially for distributed generations with intermittent nature such as wind and PV systems. In grid connected operation mode, both in dispatched and undispatched power mode, the microgrid can be used for the grid support. The microgrid will be connected to the main grid as a grid support. For example, grid voltage and frequency regulation, means it is basically supporting the grid by controlling active and reactive power delivered to the grid. Means the microgrid can complement to the main grid by controlling its real and reactive power injection to the grid, so that the voltage and frequency regulation can be achieved as desired by the main grid. Very important. This grid support will be included in the dispatched reference microgrid power in the dispatched power control mode. In an undispatched power mode, the grid support function will be realized individually through the distributed generators or storage elements or interlinked converters. Now, let us focus on the role of individual devices in a grid connected mode, and that we will discuss during the next lecture. Thank you.